The objectives for this video are to find the molarity of an unknown acid or base using a titration and describe the strength of an acid based on the molecular level. So a titration is a process used to determine the unknown concentration of an acid or base if you have a known concentration of an acid or a base. So you use a burette when performing titrations. The burette is 0 milliliters at the top, and so we start at the top and work our way down when we read it, and you want to read the bottom of the meniscus. Here's an example of a burette, and the meniscus is the bottom of the dip or curve in the liquid, and so we want to read this point on the burette. It's important to note that each one of these is about exactly 0.1 milliliters. And so as we read this burette, here is 21.0, 21.1, 21.2, that makes this 21.3 milliliters. And then that would be 21.4, 21.5, 0.6, 7, 8, 9, 22.0 is how that would be read. Here's the formula for calculating a titration. We have the molarity of the acid times the volume of the acid divided by the coefficient of the acid in the equation is equal to the molarity of the base times the volume of the base divided by the coefficient of the base in a balanced equation. Here's our first example, and the first thing you want to do is write out a balanced equation for the neutralization of HCl plus NaOH. And so we have HCl plus NaOH yields, you're going to put first and last, which gives us HOH, plus third and second, and that gives us NaCl. And then we have to balance the coefficients in front of the equation. So there's one hydrogen, one chlorine, one sodium, one hydroxide, one hydroxide. So that gives all four of these a coefficient of a 1. Everything is in a 1-to-1 ratio. So now let's identify our variables. This value here, this is the acid, and so that makes this number the coefficient of the acid. This is our base, so this number is the coefficient of our base. It says, what is the concentration of 50 milliliters of sodium hydroxide? Sodium hydroxide is our base. That makes this the volume of the base, and what they want to know is, what is the molarity of the base? So that's what I'm solving for. Then the solution is neutralized by 30 milliliters of a 0.5 molar HCl solution. Because this is the acid, that makes this the molarity of the acid, and this is the volume of the acid. So now we can plug everything into our titration equation and solve it. So it's going to go, the molarity of the acid is 0.500. And the volume of the acid is 30.0, and the coefficient of the acid is a 1, so that'll be a 1. We don't know the molarity of the base, so that's going to be my X, times the volume of the base is 50.0, divided by the coefficient of the base is a 1. And so now that we have our equation set up, we can solve it by cross multiplying. Don't start your cross with the X. We want to start our cross opposite the X. We're going to multiply 0.5 times 30 times 1. And then everything that's across with the X, we're going to divide by 1, divide by 50. So now we can type this into our calculator, and we have 0.500 times 30.0 times 1, divided by 1, divided by 50, and that's going to get us 0.3. Technically, you don't have to multiply and divide by the 1s. And so here X is equal to 0.3, and that is the molarity of my base, which is sodium hydroxide. Okay, so this says calculate the concentration of H2SO4 if 50.0 milliliters of the acid is neutralized by 10.0 milliliters of 0.01 molar sodium hydroxide. So first of all, this is my acid, which makes this the coefficient of my acid. This is my base, so that makes this the coefficient of my base. So I'm going to go ahead and plug those into my equation. The coefficient of the acid is 1. the coefficient of the base is 2. Now, when I read the question, this is my acid, which makes this the volume of my acid. Calculate the concentration of my acid, so what is the molarity? And so that's going to go here, MAVA, right? That's going to be X times 50.0. And then as I continue to read my information of the base, this is the molarity of my base, sodium hydroxide, this is the volume of my base. So this is going to go 0.01 times 10.0. Now we're going to solve this by cross multiplying. Do not cross at the X first. We're going to cross here. It's going to go 1 times 0.01 times 10.0. Then these are across with the X, so I'm going to divide by the 50, divide by the 2. And so when we calculate this, we're going to get 0.01 times 10.0 divided by 50 divided by 2. And you get 1 times 10 to the negative 3. That's the molarity of our acid. This is the same as 0.001. Here is a titration between lithium hydroxide, a 0.60 molar solution, and sulfuric acid, which we do not know the concentration or molarity of the sulfuric acid, and we're using an indicator called bromothymol blue, which is yellow in the presence of an acid. That's how we know our sulfuric acid is what's in the flask. It is blue in the presence of a base, and so it'll be green once you reach the equivalence point. So what we want to do is add our base to the acid until it starts to show a blue kind of swirling in the middle. So you see I've pulled it all the way up, and I'm adding my base very quickly, and as soon as I see some blue swirling, I'm going to back it off. Okay, so you saw the blue swirling, so I pulled it down relatively quickly. Now I'm going to go 1 drop at a time until I just turn either blue or hopefully green, which is my goal. So 1 drop at a time. And you can see how the blue starts to linger. Okay, so we'll stop right there. It just 1 drop, and it made it go a bit blue, right? But that's okay because it was only 1 single drop, so certainly not that far off. So here's the data that we have to use. We have 36 milliliters of base, 0.60 molar lithium hydroxide, 100 mils of sulfuric acid. What is the concentration? So let's do the calculation. So what we found is that we don't know the molarity of the acid. We know the volume is 100 milliliters. We know the molarity of the base was 0.6, and the titration, we determined that it took 36.0 milliliters of the base in order to turn our indicator just to blue, just past green to blue. And so the coefficient that's here in front of your acid, that's the coefficient of the acid. This 2 here is the coefficient of the base. There's our volume of acid, Ma. So we're going to fill out our equation where it is X times 100 over 1, and then the base is MB 0.60 times the volume 36.0 over the coefficient of the base, which is this 2 here. And now to solve this, you will just cross multiply. So we'll take this 1 times 0.60 times 36. We'll hit divided by this 100 because it's next to the X, and then divided by this 2 because it's across with the X. And when we type this into our calculator, we're going to get 0.60 times 36, and then times 1, divided by 100, and then divided by this 2. And so we're going to get X is equal to 0.108. I'm sorry, that is the molarity of our acid, sulfuric acid, because that's what we didn't know. And now we can check this by putting in the coefficient of our acid, which is 1, the coefficient of our base, which is 2, the volume of our base, which was 36.0, the volume of our acid, which was 100 milliliters, and then the molarity of our base, which was 0.60. And when we calculate it, we get 0.108, which is exactly what we got on paper. Our final topic is acid and base strength. and it's based on two factors. The first is the amount of dissociation that the compound goes through, and this means that the compound breaks apart into ions. So, for example, if I had HBr, which is an acid, when it dissociates, it breaks apart into hydrogen and bromide ions, and so we get the positive and the negative ions from it. Another example would be if I had NaOH, which is a base, and if it dissociates, it's going to give me sodium ions and hydroxide ions. And so the presence of this is how you know it's an acid. The presence of this is how you know it's a base. Also, we can look at electrolytic behavior, which means its ability to conduct electricity. So if you remember the light bulb experiment, if you get a bright light bulb, it must be strong. And if you get a dim light bulb, it must be weak. So strong acids and bases have 100% dissociation, complete dissociation. And so that means it totally breaks into ions. And it's going to have strong electrolytic behavior. So if we look in the box right here, everything in the box, with the exception of this one and this one, everything is a positive and negative. So we have 100% ions, which is a complete dissociation, and that makes it strong. As opposed to weak acids and bases have a partial dissociation. So it partially breaks into ions, and it's going to have weak electrolytic behavior. So over here, you can see we only have 1, 2, 3, 4 total ions in this solution, and that means that this is going to be weak. It's only got a partial dissociation. So we have few ions, partial dissociation, which is going to be weak. Now we're going to do an activity called What's in the Beaker. When I look here, because I have hydroxide, that's how I know this is a base. And you can see all the hydroxides in the beaker, which is how we know this is a base. Everything that has a positive or negative charge, I'm going to circle to kind of get an idea of how many positives and negatives do we have in the beaker. And so you can see everything has a positive or negative charge, and that's going to make this a strong base. Next, I'm going to look in this beaker, and you see how we have an H+? That's how we know this beaker contains an acid. Also, all acids start with hydrogen. Notice that everything with a positive or a negative charge, I'm circling, and since I'm circling everything in the beaker, that makes this a strong acid. Okay, over here, I have this H+. That's how I know this is an acid. And then only these have a positive or negative charge, so that means this is a weak acid. Now I'll go to HCN, and I can see this H+ in the beaker. That's how I know that this is an acid. I'm going to circle everything with a positive or negative charge, and since it's only these two and nothing else, this is a weak acid. If I look over here, because there is this hydroxide in the beaker, that makes this a base. And then everything has a positive and negative charge, and that makes this a strong base. Here, because they have this hydrogen in the beaker, that's how I know this is an acid. And then everything has a positive or negative charge, and so that makes this a strong acid. Okay, because this has a hydrogen in the beaker, that's how I know that this is an acid. And because only this and this have a positive and negative charge, this is a weak acid. This has hydrogen in the beaker, that makes it an acid. Everything has a positive or negative charge, that means this is a strong acid. And then finally over here, there's this hydroxide in the beaker, that's how I know that this is a base. Only these two have a positive and negative charge, so this is a weak base. So how do you know which beaker contains an acid? Any beaker with an H+ is going to have an acid. A base, you're going to see hydroxide in the beaker. How can you tell if it's strong? You're going to have all positive and negative ions in the beaker. And how do you know it's weak? You're going to have few positive and negative ions in the beaker.